Okay, so we talked about several of the alkenes already. We will finish that up tonight. And where we will pick up with is right here. One of the other things we can do with alkenes is we can add a halogen across it. So you can see here, you can use either molecular chlorine or molecular bromine, and that will add a halogen to each of the double bond carbon. So I'm going to show you how this works. So as always, if you have an alkene, like we've seen multiple times on Tuesday, it's the pi electrons that are going to go out and attack, right? And they are going to attack something that is electrophilic. In this case, it is the molecular halogen. And so the way this is going to work is the pi electrons are going to go out of that carbon, attack the bromine, and that is going to kick that bromine out. All right, so we're breaking the bromine-bromine bond. And so what that's going to result in is this carbon is going to now have the bromine on it, and that leaves that carbon electron deficient. By the way, the other thing that gives us is Br minus. Right? If this bromine-bromine bond breaks, notice what this arrow is indicating. It's indicating that those electrons went with that bromine, so it's now a bromide ion. Okay. Now, this is going to be a little bit different from what we've seen previously. You know, we saw something kind of similar here when we did the hydrohalogenation, right? When the pi electrons attached the proton of HBr. You know, you formed a structure kind of like this, except instead of Br here, it was an H here. Now, the difference is because bromine has something that hydrogen did not, and that is a lot of lone pair electrons. And so once you have that bromine with all of those lone pairs right next door to a positive charge, well, those electrons are going to be attracted to the positive charge. And so what ends up, you don't really end up forming what I just drew. What you really end up forming is this thing. This is known as the bromonium ion. Now, notice I have shown stereochemistry here. I put both of those bonds as wedges. I could have put them both as dashes as well. That part doesn't really make a difference. But the point is that if you have a small three-membered ring like that, if you imagine the ring as my hand, it's kind of flat like the three-membered ring has to either be above the plane of the ring or below the plane of the ring. It cannot have one bond below and one bond above. That would be way too strained. That would be impossible. Okay. So either make them both wedges or make them both dashes. They are on the same face of the ring. Okay. In the second step of this, remember, we still have that bromide hanging around, right? That Br minus is still in solution. So it's going to come in and it's going to open up that three-membered ring. So the bromide that's still sticking around in solution is going to come in and it's going to open up that ring. But because according to the way I've drawn this, the top face of the ring is blocked off by the three-membered ring. And so when the bromide comes in to attack, it has to attack from the opposite side. Yeah, you can think of it that way. And so what that results in is, the this Br that's here currently is going to end up on that carbon down there. So that's why it wedges here, it's wedged there. The incoming bromide, that second equivalent of Br, is coming in from the opposite side. So that's why I put this is kind of the new bromine, the second bromine. It is now a dash. All right, the point being, your two bromines have to be opposite each other. Now, we saw this something similar earlier, right? When we were doing remember, hydrogenation? Hydrogenation, we said that the H's add to the same face of the molecule, right? Which is why they're both dashes here, right? We called that a thin addition. We have just the opposite case with the bromination. The bromination, they're adding to opposite faces of the molecule. And so that is what we term anti-addition. So syn addition for the same face, anti-addition to opposite faces. All right. So I want to show you, this example is fairly simple because both of those carbons were the same, right? They're both secondary carbons. So the bromide could have theoretically added to where I drew it, or it could have just as equally added to that other carbon too, because they're the same as each other. But what happens if they're not? Let's look at this example. So we're going to use this as our starting material. Now, mechanistically, it's going to be the same thing. The pi electrons are going to go out and attack the bromine, and it's going to form that bromonium ion. All right. So I just happened to decide to put the bromine on dashes, meaning it's kind of going under, right on the bottom face of the ring, if you will, which means that the other group, in this case, the ethyl group, has to be wedged, right? You can't have two wedges or two dashes. If I'm saying one thing on this carbon is a wedge, then by default, the other one has to be, or if one of them is a dash, then the other one by default has to be the wedge. Okay? So now when the bromine comes into attack, it's going to make a difference as to which carbon gets attached or gets attacked, rather. Now we've seen something similar to this, right? A three-membered ring with a positive charge. You remember where we saw that? Where was it? Somewhere. Oh, there it is. Remember the oxymercuration mechanism? You have a three-membered ring with a positive charge. Remember how we said that even though when you draw it out, in this case, the mercury has the formal positive charge, that the positive charge is actually delocalized through the three-membered ring, but it's not delocalized equally. The positive charge, more of the positive charge is going to develop on the carbon that can best stabilize it. So in the same way that we said, oh, well, that carbon is more substituted than that carbon, and so this one would be more positively charged than that carbon would be. The same argument holds with bromination. We have a three-membered ring Oh, there we go. We have a three-membered ring where that positive charge is going to be delocalized through the three-membered ring, but again, not equally. It will be more localized on the carbon that can better stabilize the positive charge. So when the incoming bromide comes in, it is going to be more attracted to the more positive carbon. So the bromide is going to come in and attack right there. That's the original bromine. And so you can see that it's dashed. So as the bond breaks, it's still going to be dashed over here. Now, I told you that the two bromines have to be opposite each other. So what that means is this bromine is going to be wedged, and that means that that ethyl group gets pushed down. Yeah, Kosa. Because it's the more, this is a tertiary carbon, and that's only a secondary. Yeah, because remember, in terms of carbocation stability, the more substituted, the more stable. So that's why same kind of rule holds. If you're putting some, I mean, it's not a full positive charge, but it's a partial positive charge. So it's gonna be more stable the more substituted it is. So you're gonna have more of the positive charge on the carbon that can best stabilize it. Mhm. Yeah, yeah, you would see a 50-50 mix. Okay, questions on this? Mhm. Sorry. Uh, no, it could apply. I mean, well, the stereochemistry aspect does really only apply to rings. But the regiochemistry can apply to anything. Like you could do this reaction with something like that, you know. Um, it doesn't, yeah, I guess it really wouldn't make that much of a difference here if you're just adding Br2 across it because it would end up looking something like that. So, but where this will kind of take a turn is in this second permutation of the reaction. So in this bromination, you'll note up here, I specified the solvent. The solvent is oftentimes this carbon tetrachloride solvent. The solvent is non-nucleophilic. You can run this in water if you want. Notice it just redrew everything exactly as it was, looking at the same substrate, adding Br2 to it. The only difference is I'm switching out the carbon tetrachloride for water. So let's see what difference that makes. So the first part of the mechanism is not going to change. Pi electrons are going to go out and attack the bromine, which will result in that bromonium ion. The difference here is that now in this reaction, you have two nucleophiles. You have the bromide, and then you also have water. And in a case like this, the water will come in and do the attack. Now here again, just like before though, um, I have a more substituted carbon, which would take more of the positive charge than the less substituted. So when the water comes in to attack, it is going to attack the more substituted carbon. Oops. And then we're going to just do a minus H plus step. We got to deprotonate the water to make a neutral compound. Right? So the OH group, first of all, look at the stereochemistry. You'll notice that the OH and the bromine are anti to each other. The other thing, the OH is on the more substituted carbon. The Br is on the left. Because it's not nucleophilic. Yeah. Yeah, because CCl4 looks like this. So there's just nothing nucleophilic about it. So basically, when you do the reaction in CCl4, the only nucleophile around in that reaction is the bromide. Here, we have two nucleophiles, bromide and water. Just be in solution, kind of swimming around. But that does raise a good question. If what I just said was true, in that you have two nucleophiles, what's a stronger nucleophile, bromide or water? Well, bromide's a negative nucleophile. Water is neutral. Bromide is a significantly stronger nucleophile than water is. So why is it then that the water is the one doing the attack? It has to do with relative amounts. Presumably, if you're doing this reaction, you're going to use an equimolar amount of the alkene and the halogen. But the water is your solvent, right? I mean, you think about what that means. A solvent literally means you are dissolving something in that. You have orders of magnitude more molecules of solvent than you do of your reagent. And so just statistically, that bromonium ion is going to encounter water way, way more often than it's going to encounter the Br minus. Right? Questions on that? Okay, so those are the kind of the couple of permutations there. Let's go ahead and look at the next reaction. The next reaction is what is known as thin dihydroxylation. And what that is going to do is it's going to take the alkene and it's going to put an OH group on both of the former double bond carbon. Now, there is a couple of ways you can do this. You can do this with either potassium permanganate, which you've probably heard of before. I'm going to go ahead and draw the structures of these guys because I think it'll be helpful. So that's the structure of permanganate. Um, the other way of doing this is with a rather interesting reagent called osmium tetroxide. And osmium tetroxide, I think you'll see why they both do this once I draw the structure of the osmium tetroxide. Osmium tetroxide looks like this. But when these react, they end up making structures that look like this. So that's what's known as an osmate ester. And the permanganese would do the same thing. It kind of make that kind of same bridging type structure on the alkene. But in the second step of this osmium reaction, you end up oxidizing. You need peroxide. And what that does is it's going to end up cleaving the osmate ester. And giving you the thin vicinal diol. And the same thing would happen if you were to use the permanganate. Now, if you're, so both of these reagents will do the exact same thing. However, if you're going to use the permanganate, it is important that you specify the conditions. It has to be cold and dilute. Because as you'll see shortly, if you add permanganate to an alkene and it's concentrated and hot, you're going to get a different product. So it kind of begs the question, well, if they both do the same thing, then why do we need two things that do the exact same thing? I want to kind of list some of the pros and cons of each of these methods. So if you use potassium permanganate, number one, this stuff is it's cheap, number one, and it's readily available. Like it's a very, very common reagent. You know, you can go into virtually any chemistry stockroom or chemical stockroom on the planet, and they will 9 times out of 10 have potassium permanganate on the shelf. Um, it's relatively non-toxic, so that's always nice. However, the drawback here of using permanganate for this is that the yields are sometimes not great. With osmium tetroxide, the yields are really good. They're really high yielding, good reaction. Its drawbacks, however, are that it is very expensive. And perhaps even more so, it is really toxic. Like you have to handle it carefully or you'll die kind of toxic. But if you're just doing paper chemistry, who cares? You don't have to be bothered by things like toxicity if you're just writing out a synthesis. Okay, so what about these guys? Could you predict the products of these two reactions? Pretty straightforward with these thin dihydroxylations. You just have to stick an OH group on both double bond carbons and make sure that the OHs are going in the same direction as each other. So in the first example, you get that? Second example, do the exact same thing. Put an OH group everywhere you have where the double bond carbons are. All right, questions here. All right, then I think the last reaction we need to talk about is one that's called oxidative cleavage. Now, that name is exactly what happens. So when I say oxidative cleavage, the cleavage part means you're going to break the molecule apart at the double bond. And then each of those former double bond carbons will get oxidized. Okay, hence the term oxidative cleavage. So if you look at what this is showing you, so we're just I've got a couple of different alkenes here. Notice the different substitution levels of the alkenes. But in all of these reactions, we are splitting the alkene in two. Now, I've got two different kind of panels here because there are two different ways that you can do oxidative cleavage. There's a milder form. And then there's the harsh form. Notice the difference. In the mild form, we are making aldehydes and ketones, depending on the level of substitution of the double bond. But everything shown here is aldehydes and ketones. Under the harsher form, you cannot isolate aldehydes. So you'll still get the ketones that you got in the mild form. But the aldehydes, well, they'll form initially, but under these strong oxidizing conditions, aldehydes get oxidized up further to the corresponding carboxylic acid. So whereas the mild version of this reaction gave aldehydes and ketones, the more vigorous, the harsher, more strongly oxidizing conditions will give you ketones and carboxylic acid. All right. So go ahead and give you the reagents. The harsher form is something we've seen before. That is done with potassium permanganate. Only this time, instead of cold and dilute, we're going to have to run it hot and concentrated. So that's why I said a minute ago, you need to specify conditions when you're using permanganate. The more mild form of this, we're going to use ozone. So it's what's known as ozonolysis. So I want to look at a few examples of this reaction because these can be a little bit tricky at first. Let's go ahead and do this one. So the way I do these is in all cases, you're going to break the molecule apart at the double bond. And I usually kind of think about this as a left half and then the right half, right? The product that comes from the left side of the molecule and then the product that comes from the right side of the molecule. When you go to draw products, it's pretty straightforward because all you have to remember is that instead of having a carbon-carbon double bond in the product, you're going to replace that with a carbon-oxygen double bond. So let's go ahead and predict the products of this oxidative cleavage. So the left-hand part of my molecule is going to look like this. Now, it was that carbon that I highlighted in green there, that was the carbon that was double bonded to the other carbon. So in the product, I'm just going to put it double bonded to oxygen then. That's one half. Now we're going to do the right-hand half. So the right-hand part of this molecule is just, what, 1, 2, 3 carbons? 1, 2, 3. And then here again, it is that carbon that used to be double bonded to the other carbon. So now it is going to be double bonded to oxygen. Now, the last question we have to ask ourselves is this thing, because it only has one carbon group on it, is this going to be an aldehyde or is it going to be a carboxylic acid? Yeah, it's going to be a carboxylic acid because we're using the harsher oxidizing condition. So I need to make that OH there. All right, questions on how we did that? All right, go ahead and try this next one. See if you can give the ozonolysis product of this alkene. All right, so we are splitting at the red line at the double bond. And so then the left-hand part of this molecule is going to look like this. And it was that carbon that was double bonded to the carbon in the reactant. And so that means it needs to be double bonded to oxygen in the product. All right, so again, that has one alkyl group on it. So the question is, do I want to make this an aldehyde or a carboxylic acid? Yeah, this is going to be the aldehyde because this is the milder form. And then we've got the left-hand part of the molecule, or sorry, the right-hand part of the molecule now. Looks like that. And it was that carbon that had the double bond to carbon in the reactant. And so that needs to be double bond to oxygen in the product. And you can check yourself with these reactions too. Remember, all we're doing is breaking the molecule apart. So if I have 8 carbons in the reactant, I better end up with a total of 8 carbons in the product. All right. One of the more common mistakes people make as they start doing these. It's easy if you're, especially if you're in a rush, to either add or drop carbons. Mm-hmm. No, in fact, well, actually, I'm glad you brought it up because I think, oh no, we'll look at an example of that in just 1 second. I think that's the next example. Okay, try this one. This one has 2 double bonds in it. By the way, how many products are we going to get from this, do you think? You would get the left-hand piece. That would be one. And then you would get the space between the lines. That would be two. And then you would get the right-hand piece, which would be three. So you should have 3 products of it. All right, so my left-hand piece is going to look like this. And because this is ozonolysis, that means we're going to make an aldehyde. The central piece is one, two, there's 4 carbons. And then the right-hand piece is going to look like that. Mhm. Correct. Yeah. If you didn't have Like say that methyl group there, that would give you, I would actually just give you two molecules of acetaldehyde. Mhm. By the way, one thing I didn't mention earlier, with ozonolysis, you need a step two. You need a reduction step. And that reduction step is usually either going to be this compound here, which is called dimethyl sulfide. Um, I have it abbreviated up there, DMS, it stands for dimethyl sulfide. Sometimes you'll see zinc used as well. Any questions on this one? Uh-huh. Hmm. Yeah, I probably wouldn't count off for it, but it would be more correct if you had the step two dimethyl sulfide. Okay, here's your ring. So what what is going to happen to this ring, by the way? Yeah, it's going to cause the ring to bust open. Now, by the way, I think I may have made this suggestion before, and I'll make it again. Anytime I'm dealing with any kind of a ring, whether I'm breaking rings or I'm making rings, I always number my carbon because it's really easy to get mixed up with positions when you're making and breaking rings. And so I just kind of just arbitrarily number them. I would do this like as a one, two, three, four, five, and six. Hmm. Oh, it doesn't matter at all. There's absolutely no reason or rhyme the way I did it. I just number it and then be consistent with the product and number it in the same way. You can number it any way you like. Right, so the top piece is pretty easy. It's I think it's pretty straightforward to see what you're going to do with the hat here. That's just going to cleave off and give you a molecule of acetone. Now, the trickier part is what to do with the ring. So clearly not going to have that three carbon thing sticking off of it anymore. But because we are breaking that, as I've numbered it, 1 to 6 bonds, that means we're going to end up with a chain, right? It's no longer a ring. And so I'm going to have a 6 carbon chain. 1, 2, 3, 4, 5, 6. So just go ahead and draw that. And I'm going to number this consistent with the way I did the other one. Now we have to figure out where the double bond, the oxygens go. So, how many how many CO double bonds are we going to have on this chain? Yeah, I'm going to have 3 of them. Because remember, everywhere you had a CC double bond, you need to put a CO double bond. So I had a CC double bond at C1. I had a CC double bond at C2. And I had a CC double bond at C6. That's it. Any other questions on this one? All right, the last example I want to look at with you flips the script a little bit. There's your product. What did it come from? Basically, any CO double bond that you have in this molecule used to be connected to another CO double bond through the CC double bond. So I don't know, maybe the first thing you want to try is, okay, well, I've got a CO double bond there and a CO double bond on the other end. Did they used to be double bonded to each other? So think about what that would be. If this carbon were double bonded to that carbon, that would give me a ring that is 1, 2, 3, 4, 5, 6. That's a seven. That would be a seven-membered ring. Mm, that's a little unusual. And then, in addition to it being a bit unusual, is what's going on with those two things? So I don't think that this carbon was double bonded to that carbon. So what are our other options? Could this one be double bonded to that one? Or this one double bonded to that one? Those would be the only other two options. Okay, let's think about that. If this were double bonded there, what ring size would that be? That would be a 1, 2, 3, 4. That would be a five-membered ring. That's not too bad. We've seen those. Well, if that's the case, if those two were double bonded, then that means this one must be double bonded to that one. So what would that give you? That would be a 1, 2, 3, 4, 5. That'd be a six-membered ring. Perfectly normal. So I think that's what's going to go on, right? I think that's so we're going to end up with a five-membered ring next to a six-membered ring. So I'm definitely going to number my carbons for this because it's kind of confusing me. So let's number the five-membered ring in red. And I'm going to number the six-membered ring in blue. So here again, we're going to have a five-membered ring fused to a six-membered ring. So I'm just going to draw the skeleton, and then we can worry about putting in the stuff later. Okay, so that is what I just described, a five-membered ring fused to a six-membered ring. Now, when I go to number them, again, I'm going to try to number that system the same way that I did originally the product. Notice the shared carbon. Carbons 4 and 5 are being shared by both rings. So I need to make sure I'm consistent with that. So that's carbon 4, that's carbon 5 of the 6. Carbon 4, that's carbon 5 of the 5. And now it doesn't really matter. This is going to be 3, 2, and 1. And then this is going to be 3, 2. Where does your double bond need to go in the 5-membered ring? Yeah, between carbons 1 and 5. Where does the double bond need to go in the 6-membered ring? Yep, between 6 and 1. That'd probably be good practice for you to think about this in the forward direction. If I start with this and try to do that oxidative cleavage, do I indeed make that? All right. That's something maybe you could work on. But I think so. I'm reasonably confident, but you can verify. Okay. We've got about 10-ish minutes left. So with that time, but that basically takes us through the end of the alkene chapter, all of the alkene reactions. With all of this, you should be able to do homework number 1 that we'll cover together in lab on next Tuesday night. But I do want to introduce you to another type of problem that is quite common with all of this. And they're pretty fun. Boy, let me make sure I don't have the answers written. You have the answers written. This is a reaction map. And so you can see that in this, you are given some things and missing others. And it's your job in a reaction map to figure out what's missing. Now, in a reaction map, there's no rule that says you have to start at the beginning and work your way to the end. You can start anywhere you want. In this particular example, it's not too bad. You could probably be pretty straightforward to start at the beginning. But sometimes, as you'll see, we're going to look at several of these in the near future. Sometimes it's impossible or difficult to start at the beginning. You have to kind of start somewhere else where there's a more concentration of information. But in this one, it's going to be pretty straightforward, I think, to start at the beginning. So go ahead and get into it. So what we're looking at is we're given the starting material and you're given the product of reaction 1, and we're just missing the reagent. So what is letter A? What is the reagent that will take this compound to that compound? Well, here again, the big clue is that you're starting with an alkane. Well, really only one thing you can do with an alkane, and that is photobromination. So A is going to be bromine and light. And notice where the bromine ends up. The bromine ends up at the most substituted carbon position, which it should. All right, so well, we're getting into a bunch of nothingness. Uh-huh. Oh, yeah, I mean it doesn't I mean those positions are equivalent to each other. So, I mean, if you put the bromine there, you put the bromine there, you get the identical molecules, the identical product. All right. Well, hmm. What do we do from here? Hmm. Well, I mean, it's possible, but I don't really know that for certain because we're moving into like three consecutive unknowns. I think what I would do in a case like that is start at an end and kind of start to work your way back. So the reason I say that is because look at this product. The product is a ketone. We've only seen up to this point one reaction that generates a ketone. What reaction was that? Yeah, was the oxidative cleavage, right? So if that's true, an oxidative cleavage reaction by definition makes two molecules. But wait a second, I only see one. What does that tell you? If you're getting only one product from an oxidative cleavage, that tells you that the cleavage must have been done on a symmetric molecule. So basically, you're getting two compounds, but they're just the two of the same compound, right? So so I would need to put a double bond, draw it this way. Remember, we're just going to replace the CO double bond with a CC double bond. So we should end up getting something that looks like this. Right. So that should be letter C, right? Because can you see how if I did the oxidative cleavage of that, I would get two molecules of the butanone. Okay, so that's going to be my letter C. Okay, what's letter D? We've kind of already talked around it, but it's an oxidative cleavage reaction. So what specific reagents do you want to use as letter D to do this oxidative cleavage? You got two choices: permanganate hot and strong, or the ozonolysis. Yeah, really doesn't matter because we're not making aldehydes or carboxylic acids here. So you can use either one. All right. Well, then what do we have? Let's go down to E. How can we take this thing and make it into that thing? Actually, I'm going to fix my double bond so that it's more in line with the actual product. What reagent can I use to take this and make it into that? Well, that's an old one. That's a unit 3 one. I'm putting a bromine in the allylic position. Sounds familiar. An allylic bromination. India. Okay, one step left. How do we take this bromine and make letter C that alkene? It's just an elimination. So do you want to use a regular base or do you want to use a bulky base? Which one? Yeah, we were trying to get the Zaitsev product here. So we're going to use a regular base. So you could use, I don't know, something like methoxide maybe. Mm-hmm. Mm-hmm. Oh, so NBS is for allylic bromination. So remember, when you have, so the allylic position is the position next to a double bond. So we have allylic positions at all those places. The allylic bromination is a radical reaction. And so just with as with all of those radical bromination reactions, it's going to be selective for the more substituted carbon position. So you're not going to see, I mean, basically those two positions, those primary allylic positions are identical to each other. And so are those two secondary positions. They are identical to each other because of the symmetry in the molecule. So you basically have two options. Do you want to put the bromine at the primary allylic or do you want to put it at the secondary allylic? And so you're going to see a preference due just to radical stability for the more substituted position. So that's why we're ending up with it at the secondary allylic position. All right. Any questions there? Okay, so we'll look at a few more of these reaction maps as we start learning more reactions, because you will definitely be seeing these problem types on exams. It's a very common way of just kind of testing your skills with reactions. All right. Okay, it's probably a good place to stop. So I will see you in about 10 minutes over in the lab.